Recording in progress.
Hello everyone. Okay, good to see you all. Sorry for the slight delay. I was getting all of the grades working. So let me see. So the exam actually has been graded at this point, and I'm not sure if people were able to pull up the grade information. I actually, our TAs are helping to put it into the canvas so that you'll be able to see it there. And let me see if I can get you something here also to share. Yeah, so the first question I have is, are people actually able to see their grades somehow on the exam? I want to know if that one got pushed all the way through. Yes, okay, good. And just out of curiosity, did it send it by email to you guys? Are you looking at it in Gradescope, or are you looking at it in Canvas, or both? Or that will let me know. Gradescope, okay, yeah. So the Gradescope thing got published earlier, but I think the relevant thing is also how did the class do on this? I learned a lesson. The exam was too hard. So, and the point of this class was not to make life too complicated. So, this is actually what we see in the exam results. So the exam results look something like this, where it looks like somehow 3 questions was actually quite hard to achieve. 2 questions was what most people, I guess, achieved. I think, if you wanted to know how you did on this exam, if I was just going to do some grades right now, I would probably put like, the cutoff for A to B would be somewhere in between 20 and 30 points. Actually, that is about what it normally is. So maybe in that case, I'll say the exam was actually possibly in line with what other years have been. So if I was looking at this, I'd be like, yeah, maybe about from here on over, if those are A's, that would be reasonable. And the B range would be somewhere around here. And maybe the C range is like if you, I don't know, got at least 10 points or something. That's maybe how I would think about this. And the good thing about this kind of a grading scheme is that hopefully, well, there are going to be 3 of these midterm exams, and then there will also be the final exam. All of these give you opportunities to add up like 10 points or so. So, I mean, my general thing is it's, the exam is that somehow the A cutoff was around over here, so the B cutoff would probably be around over here, and then the C cutoff is probably around 10 or something. And the hope is that if you understand the course, then as you do the other exams, you'll be able to pull yourself up. I wanted to pause here though and say a little bit and open for if people have any questions about how grading is usually done in this class or what the expectations are. The important thing is that getting a score of 50% on this exam is like actually very good. So that's the exam was designed in a way where some of the questions are actually intended to be quite challenging. I was actually surprised that people got scores that close to 50. So, question. Chris, do you want to just go say the question out? Because my reading is not very good.
How should we go about asking TAs how they graded the exam?
Oh, yeah, that's a good question. I would ask the TAs. There will be a recitation tomorrow, so if you can ask them if you have any questions. They actually graded all of the questions except for question 4. So on this exam, I graded the question 4. Question 4 was this one, which was the rhombus on Pascal's triangle, the very top part. And so that one I took care of. So if people have questions about that particular grading, that would come over to me. I'll be happy to answer. But one thing that helps this time is that we're using Gradescope, so there's actually some uniformity to grading. Because the way Gradescope works is there's this rubric, and it's like you get points for very specific things. How do regrades work? Yes, Aaron, just ask your TA, and if you have a particular question you'd like to have looked at again, we're actually very happy to look at it again, and we can go and see how that is. Yeah. I just really wanted to emphasize though, like if you're used to doing exams where somehow a lot of people get 90%, that is not how the exams in this class work. But on the other hand, there's like a massive curve that we put on the class. And the reason we do this is because actually it makes it, in some sense, it makes it easier to make sure you got the basic stuff and you don't have to worry about a few like super high scorers just filling up the top. The top is kind of unbounded out to here. So that's how it is. And the other reason I do it this way is hopefully it makes it harder to cheat on, in the sense that in this particular exam, everyone was really working all the way to the end, and it's not, you hopefully shouldn't have to worry as much about cheating issues because there isn't any like collaboration opportunities during the time period. Any other questions about the exam? The TAs will be talking about how to do the questions tomorrow. The questions are actually, some of them are actually pretty interesting. So I won't steal their thunder, but there's actually a lot going on this test. And you know, if you did get 3 of the questions, that's very legitimate. And if you got anything more than that, that's very impressive. If you got all 5, that's very surprising. So, yeah,
I have a question.
Go for it.
I got here late, so I don't know if you said this, but did you say like what the mean and median scores were?
No, I didn't, because I don't know what they are. So, I mean, you got here late. I got here late also. I was quickly trying to export this picture so that we could have it to look at. I mean, if I was to look at this, the way I would explain it is it looks like there's a uniform distribution with a spike at 20 something. So I would guess that the mean and the median are all around like 24, 25-ish. Maybe 24, maybe 23, something like that. Because you could just see, it's basically spread across, except for there's a lot of people got just over 20. Oh, I should say a little bit about how the scoring works on this exam. In all of my exams, the way that partial credit works is it's related to whether or not you basically got the idea. And so even if you got the whole idea and you just like made some calculation mistake at the end, you'd still get like 9 points out of 10. Or 10 points out of 10 in some cases. On the other hand, if you had a lot of stuff that you wrote down, but it didn't seem to be going in the direction that would help, there isn't actually lots of partial credit that goes towards those ideas. The idea needs to be somehow relevant to the particular question at hand. Yeah. Okay. Any other questions? If not, let's just continue on and talk about some topics in the class then. Okay, so today we're going to move into another direction. So we're going to move into another topic of the entire course, and this topic of the course has to do with counting things, but we're going to count things in a more complicated way. So the way that I want to start for this part of the course is, let's start with a question of something to count. And the good thing is that, not the good thing, but like we're doing some totally new unit than the previous unit. So we're going to have a very different flavor of questions and everything as we go on out. And then the old unit you'll see again on the final exam. And of course, we'll still be using those ideas throughout. But the new question that starts this whole thing is, how many ways are there to tile a picture that looks like this? And the picture that looks like this is, it's got n squares across, 1 square up and down, but only using these 1 by 1 squares and 1 by 2 squares. They're not squares, they're dominoes. Oftentimes these things are called squares and dominoes. So that's the question we're going to do here. I'm going to say some people have seen this before. If you've seen it before, please don't give it away. But what we're going to do is we're going to let everyone who hasn't seen this before start to play with this question. This is actually a very interesting question. So if you see a question like this, what would you want to do at the beginning? I'm intentionally asking people who don't know the answer. If you don't know the answer and you saw a question like this, what might you want to do at the beginning? And a hint is that somehow when you're doing a combinatorics problem, and actually it's a useful exam strategy too. Ben, do you wanna jump in? What might you want to do?
Test for like small cases of n.
Yes.
And then see if there's a pattern.
Small cases. I want to give that as an exam strategy. Like on my exams, oftentimes there's something where there's a pattern. And so if you, like for example, that Pascal's triangle thing, if you worked out a few of them, you might have noticed a pattern, and then you can use the pattern to solve the problem. That's a good idea. Let's try to find small cases. What's a good small case? N equals 1. Okay. If n equals 1, how many ways are there? Well, let's see. We can do this together. How many ways can you tile a 1 by 1 where you use like squares and dominoes? Really, there's only one way. It's just the one square, right? So there's one way. One way. Actually, I'm going to draw the one way, and then I'm going to draw an arrow to the 1. That is one way. Okay. Now what if I do n equals 2? What could this be? It's saying.
Can we use like one domino or like two squares?
Yes, you can use one domino for 2 squares. That's one way.
Yeah.
But there are more ways. So if I have a 2 by 1, what else could I do?
Two squares. Like
2 squares. Yep, 2 squares. And so that gives you 2 ways. Okay, n equals 3. How do I do n equals 3? Charlie.
You do 3 squares,
3 1 by 1 squares. Yeah.
domino square,
Domino square.
or square domino.
Okay. Square domino. 3 ways. Okay, so what's the pattern? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So that's the answer. Well, probably not. Otherwise, that would be too easy. So we need to do another one. let's do the next one. N equals 4. Yikes. How do you do this? Sydney.
Maybe like look somehow at the last 2 cases and then like add things to it in particular places.
Oh, what do you mean exactly by the last 2 cases?
Like so n equals 2 is like when you have, it's the last time that you have an even number of squares, and then n equals 3 is like the last time you have an odd number of squares. So then you can like insert the corresponding thing somewhere in there maybe.
Okay. Last odd, and somehow insert. I'm writing all these ideas, okay? Interesting. Anyone else want to like build on this thing or like give me an exact answer for how many ways there are to do it for? I'm always trying to get new people involved. Martin?
So you just take the n equals 2, add like another domino, and then you take the n equals 3 and add another square.
Oh, okay. So you're saying that you can do this with adding another domino, or you can do the n equals 3 with adding another square. These are, by the way, how you would construct all the n equals 4s. So actually, this turns out to be that the next number is the sum of the previous 2. Quick question: was this topic actually already covered in concepts? This idea of like the squares and dominoes? No? Okay, you just come up with it. That's even better. All right, because I now saw like 2 independent ideas coming up with this like, oh, you can build from the previous ones. That's cool. So it is actually true that the answer for n equals 4 is the sum of 2 plus 3, which is 5. And that's the Fibonacci sequence. All right, so that's the Fibonacci sequence. And in particular, if I'm looking at this particular at the sequence, we need to have a very clear proof of why this is the case. What you just said is you can build the next one from the previous things. That is correct. But whenever I'm counting something, I usually want to talk about it as I'll decompose into cases, and I count each case. I'm always afraid of saying I can build all of them this way because I need to know that I've built all of them. Like I need to know that I didn't miss any. is the main problem. So I want to use this idea, but I want to say it in a slightly different way. You're looking at the last thing. You're like, how do I do n equals 4? Let's look at what's happening at the far right. Here's another way to explain. For n equals 4, what happens is that, well, you have this big thing. It's 4 across. Okay? And there's two cases. The thing at the very, very end is either a square or a domino. Has to be one of the two. So there's a case 1. The rightmost is a square, 1 by 1 square. And then we'll have a case 2. Rightmost is a 1 by 2 domino. And the important thing is, once you see I've split it this way, it's very clear. It has to be exactly one of those cases. If you have one of these pictures, has to be in exactly one of those cases, can't be both. Now if I do each one separately, in this one where the rightmost is a 1 by 1 square, now what do you have? So here's the square on the right. That's supposed to look like a square. Here's 3. And the important thing is, how do you fill this? Well, you fill this with however many ways there are to do the n equals 3 case. So this one is fixed, right? And you can finish it in the number of ways for n equals to 3. That's the key. And then over here, the second one, it's the same idea, but now we take the rightmost. The rightmost is 2 squares. So that, it's a domino, right? And then you can finish it in the number of ways for n equals 2. And so that's actually how this works in general. Because if I have any n, the important thing is that this first one is like n minus 1, and the second one is n minus 2. So that's how you find out that this satisfies the Fibonacci recurrence. This thing is actually going to satisfy the same recurrence as some famous sequence of Fibonacci numbers. The Fibonacci numbers, the way I usually like to write these is I personally prefer to say that f sub 1 is equal to 1, f sub 2 is equal to 1, f sub 3 is equal to 2, f sub 4 is equal to 3, and f sub 5 is equal to 5. There's a reason I like this. The reason is because if I write things this way, with f1 being 1, f2 being 1, it's actually quite natural, just for the heck of it, to add an f0. f0 is useful. If I want to make a sequence of numbers so that the next number is always the sum of the previous two numbers, well, actually, you can extend it backwards if you wanted. And this does not actually count anything in specific, and in particular. It doesn't count anything in particular. But does anyone know what number you could write for f0 so that somehow it still satisfies the recursion that I want? Chris?
So you could do 0, but this also reminds me of Pascal's triangle, because every row above the one in the row is 0.
Yeah. So the thing is, like Pascal's triangle, also it was counting something, and then for all the stuff outside, we could just define the numbers so that it still satisfied the recursion. In Pascal's triangle, by the way, it made sense. Did you know how many ways there are to pick 5 things from 2 things? Well, 0, of course, right? That makes sense. Over here, the thing is that Fibonacci wasn't really counting anything anyway, right? So it's just useful. You could say f0 equals 0. It's useful for the purpose of a Fibonacci sequence. And what this satisfies is it satisfies the Fibonacci recurrence, fn plus 1, well, let me call it fn. Fn is equal to fn minus 1 plus fn minus 2. Okay? And now, if you have this Fibonacci recurrence, it turns out that it's then very easy to prove by induction the answer to the tiling problem. So now let's compare to the tiling problem. So the number of ways to tile like an n by 1 is, can anyone tell me what that is? If I have an n by 1, it will be a Fibonacci something. Fibonacci what? Because we saw like the 1, 1, 2, 3, we saw the 1, 2, 3. So what is this? Venkatesh.
It'll be Fn+1.
Okay, Fn plus 1. So the reason we know this is because we were looking at the weird answer. The answer was that n equals 4. We know that the answer for n equals 4 was 5. We already figured that out last time by adding the two previous ones. So if that was 5, I want that f sub 4 is 5. I want the answer for n equals 4 to be 5. And 5 is f sub 5. So it's the f of n plus 1. That's correct. And if you wanted to prove this by induction, you could. The way you prove this by induction, well, let's do that as an exercise. How would I prove this blue thing by induction? Well, if I have induction, I need some base cases or case. What do I need for this? How do you do this by induction? Jack.
I mean, I would just begin by doing what we did in the last slide. Just show the one by one tilings, and I think that should be sufficient.
Yeah. So you show these. Okay, look, we got these. But the reason I'm asking this question is, how many base cases do you need? And what kind of induction are we doing anyway? Do you know what I mean? I'm like reviewing induction. What's induction? Induction. Yeah, we need a strong induction. Okay? So we need to use strong induction because we need to know something about the number of ways to do like fewer things. Let me use a new screen because then that will be more space. Okay? So what I'm going to say is the fact. And this is a useful thing to know because if you ever have to prove one of these by induction, this is how you do it. The fact is the number of ways to tile this n by 1 is f sub n plus 1. Okay? Now we have to do a proof. And we use strong induction. Now the base cases, which ones do you need? N equals like how many n's do you need for this base cases to be established? Jack, do you want to give us a number? Because we did 4.
2, right?
2.
The idea is that, we're using the recurrence, which needs the last 2 terms.
Yes.
You need to establish 2 to begin with.
Yes. And the induction step, now I'm just doing this fast. I just wanted to use this to review the fact that you actually need 2 base cases. And the reason is because if I only had 1 base case, exactly as you say, the next number is the sum of the previous 2. And I need to know that both of them were what I wanted. Okay? So n equals 1 and n equals 2, we did those already. Okay? We did those. They matched. Okay? And the induction step is to get n, to get the number of ways for this n by 1, we can use the answer, use the known fact for all smaller values of n. Use the known fact for all smaller values, which are less than n. Okay, and the way you do that is exactly what we just saw with those cases, right? So we saw that there's those ways. Those ways split into the 2 cases. I'm just writing it fast now. Like one of the cases is where you have a 1 thing at the end, n minus 1 in the left, and the other one is where you have a 2 thing in the end, and n minus 2. Right? This is exactly what we saw before, and I'm not writing all those words because it's the same reason. Now the thing here is that this is going to become the number of ways for n minus 1. That's where you use the inductive hypothesis. Ind hype means inductive hypothesis. And I get that this is f sub n minus 1 and then plus 1. And the second one is f sub n minus 2 plus 1. Right? I'm just doing this whole thing very slowly just because we're at the beginning of this recursion section. Okay. Ooh, did I make a mistake? Doesn't normal induction... Yeah. Thanks for answering the question in the chat, everyone. So it's because I need to use the induction hypothesis for a few of them. You see, I've just used induction hypothesis both for n minus 1 and for n minus 2 together. And since I used induction hypothesis twice for different values of n, different values, that's why I want strong induction, so I know that each of them work. So now what I know is that my answer is the sum of these 2. And if I know that the answer is equal to the sum of these 2, that's f sub n plus f sub n minus 1. And now here is where you use the definition of the Fibonacci's. F sub n plus f sub n minus 1, that is exactly equal to f sub n plus 1. That's not by induction. That's by the definition of Fibonacci. Right? And then so from all of this, then I've actually managed to prove exactly what I wanted. I got it for the n. So this is like an example of how you'd write through the entire induction proof for something like this, if I wanted to know how many ways are there to tile this particular thing with this n long strip with squares and dominoes. Okay, now why would anyone care? Well, that's a good question. One reason is because it's just neat. The more ways you can see that things are equal, the more things you can prove. We'll see more reasons later. But before we go there, let's go and start talking about some of these reasons why the Fibonacci sequence is neat. One of the reasons is that the Fibonacci sequence actually has some nice coincidences all through it. Fibonacci. So we've got some nice things here. Let me write the sequence again, just so that we can have it in front of us. F0 is 0, F1 is 1, F2 is 1, F3 is 2, F4 is 3, F5 is equal to 5, F6 is equal to 8, I want one more. F7 is equal to 13. Okay, I've got all these Fibonacci's. Now let's just start doing some stuff for fun. Hey, let's pick something randomly in the middle, like 2 and 5. What happens if I multiply 2 times 5? Well, that's 10. Okay. Neat. What happens if I multiply 5 times 13? I'm going to do that one for fun. That's equal to 65. Does anyone notice anything neat about the numbers 10 and 65, especially as related to other numbers that are inside this table? I'm looking for a coincidence. It's just like, by the way, how to do these like random exam questions about Pascal's triangle or Fibonacci sequence. It's like, is there some interesting pattern? I see a 65. 65 is a really nifty number. Is there anything about 65 and like any other number that you can see here that you might say, I wonder if there's a coincidence? Any interesting facts about the number 65? Dhruva.
It's 1 more than 8 squared.
Oh, it's 1 more than 8 squared, isn't it? So here's an 8. That's 8 squared plus 1. And Dhruva, why did you think that was a neat thing? What else do you see here?
Because 3 squared plus 1 is 10.
Oh, wow. Actually, 10 is equal to 3 squared plus 1. My gosh, does it keep working? So F8 is equal to 21. F9 is equal to 34. Oh no, I actually don't know how to multiply those numbers. 13 times 34. Okay, I'll just do it. 34 times 13. 4 times 3 is 12. 9, 102. Do I believe that? Yeah, okay. 34. 442. Does that make you happy? 13 times 34 is equal to 442. How many people like this? Ah, this is good. This is good. Actually, 21 squared is 441. Okay? 21 squared plus 1. Okay, 21 squared, by the way, is neat. If you want to multiply 21 by 21, you actually get the same, you get the same multiplication as you do with 12 times 12, just flipped in order. And that's why the answer is 144 flipped. That's actually why 12 squared and 21 squared are like flipped. Whenever you do some kind of a perfect square, a 2-digit perfect square, and you have no carrying in the multiplication process, then you'll see this flip. So for example, 31 squared is 961 because 13 squared is 169. But anyway, fun stuff. Okay, QED, baby. What is this? Vacuously works for 7, so this must be true. Love it, love it, love it, love it. Okay. Okay. So yes, the n equals 7. We gotta do it. We gotta do it for 7. Okay. All right. So it looks great. Looks like we found a really interesting pattern. Yeah. So what's the conjecture? Anyone have a conjecture? What's the conjecture? What should we say? Is there a conjecture? Raise hand, Advait.
Okay, so if you take like an odd Fibonacci.
Ah, an odd Fibonacci.
Sequence and like the next odd one, like it'll be times odd plus 2. It'll be like
Oh, odd plus 2, I like it. That's next odd, isn't it? So odd plus 2. Uh-huh.
And then it'll be equal to f odd plus 1 squared plus 1.
Plus 1. Do I have space? Plus 1. Okay.
I say this because if you try it for convenience, if you try it for the even one, you get minus 1.
Ooh.
Pretty cool.
This is pretty cool. So first of all, I drew all of these things so that they didn't overlap, okay? But it's very dangerous to go and make things, to make a deduction of stuff only by doing like the odd ones. You should also double check what happens with the even ones. And 3 times 8 is equal to 24. Now 24 is not 25 plus 1, but it's 25 minus 1. Okay, so that's 5 squared minus 1. That's interesting. And if I go and take like 8 and 21, I can do that. That's 168. That's 169 minus 1. That's 13 squared minus 1. Neat. So what we found out is that there's another conjecture, which is that f even times the next f even times f even plus 2 is equal to f even, now I know I need more space, f even plus 1 squared and then minus 1. Fibonacci is full of these kinds of patterns. All right, how might we go about proving something like this? If I want to go and prove something like this, induction again. Okay, let's go and try induction again. Okay, so how would I try to do this by induction? The conjecture, by the way, is like f and f the next has something to do with f the next minus 1. All right, we basically have 2 conjectures, by the way. Do you want to do that? Actually, just a quick question. Advait says induction again. Do you want to do induction from n to n plus 1? Do you want to do induction n to n plus 2? Do you want strong induction? You want n to n plus 2, right? Because you're like, let's just do the odd ones first. How about that? Advait's idea would be, let's just prove it for the odd ones first. Maybe we'll need the even ones also. We'll find out. But let's just try it for the odd ones first, and then let's see if it works. Okay. So let's do this fact. Okay, let's do it for the odd ones first. F odd plus times F odd plus 2 is equal to F odd plus 1 squared plus 1. Proof. Induction. Okay, now I usually do this induction thing at the beginning when I'm trying to make a proof. I don't get all confused with n's. I just want to see how you get like the induction hypothesis to work for something like 7. Okay, so the thing is like the base case. We better believe the base case, or else you don't. With induction, if the base case is false, don't bother doing anything. All right. So the base case better be easy. Base case. What is that? I'll do that since that's easy. That's f1 times f3. What is that exactly? That's f1 was 1, f3 was, what was it? Let's look. 2, f3 was 2. 1 times 2, okay? And on the other hand, I have this f2, that's odd plus 1 squared plus 1. Oh, let's use a different color so it's clear I'm working from 2 different sides. That's how I like to think of this. I'm going to try to make them meet in the middle. It's like if you're building a tunnel through the mountain and you want it to meet in the middle, that's basically what we're doing. Not sure if that example made any sense. But okay, so I've got f2 squared. F2 is, what was f2? I forgot. F2 is 1. Okay, so this is supposed to be 1 plus 1. Yay, the tunnel met. 1 times 2 is equal to 1 plus 1. That proves the base case. And the feeling you should have is the same feeling as when 2 people are drilling through a tunnel and through a mountain and they meet in the middle, they're very happy. Because if they didn't meet, then it's just terrible. But anyway, so we have this thing. And actually, I've often wondered, how did they manage to drill through mountains like before they had fancy electronics and actually meet in the middle? That is incredible. Okay, separate issue. Let's continue. So it works. What's the inductive step? Induction step. I never know whether it's called the induction step or the inductive step or whatever. So I usually write IND step. But whatever the inductive step is, how do you do it for 7? How would we get f f7 times f9 equals f8 squared plus 1. I get to use, like using f smaller stuff. Get to use f smaller odds. All right? That's how I come up and invent a proof. It is not legitimate to say, well, I happen to know what f7 is, and I happen to know what f9 is, and I know what f8 is, and look, it works. Induction means I need to be able to reduce them down. Ideas? Advait is here.
You can try writing F7 and F9 in terms of the previous.
Okay. The only thing I know, really, so far, about Fibonacci's, that was supposed to say Fibonacci's, is that, you know, like this F, do you want to take apart F7, F8, and F9, all three of them, into smaller things?
Sure, why not?
Sure, why not? Okay, I know that the F7 is equal to F5 plus F6. And I know that F9 is equal to F7 plus F8. And I know that F8, that was a 9. F8 is equal to F6 plus F7, okay? So it's enough to prove. Let's substitute them all in. I need to prove that F5 plus F6 times F7 plus F8 is equal to F6 plus F7 squared plus 1. Do we have a hope of doing this? My hope is to find some way to say, oh, look at this green algebraic expression. I can recognize in there some stuff which is like previous statements. The previous statements would be things like saying, I don't know, f5 times f7 was f6 squared plus 1. Can we try to use that stuff to put this together? Maybe this will actually work. Anyone else want to jump in on how you might try it? We get to use anything from before. We're trying to prove this green statement. Jyotya.
Well, we can try to distribute out the multiplication first, and then we'll probably find that,
Yeah, distribute out, look for coincidences, look for cancellations. I'm going to recopy the green thing onto the next screen, okay? So the green thing is, here's what we want. I always distinguish between what we want and what we have. What we want was f5 plus f6. And then it became f7 plus f8. We want this to be equal to f6 plus f7 squared plus 1. And what you were going to say is, well, that's equivalent to distribute out the whole thing, because the left-hand side is the same thing. We're not changing anything. f5, f7. I'm not writing a times sign anymore because we just stuffed them next to each other. Plus f5, f8, plus f6, f7, plus f6, f8. I need that to be equal to f6 squared plus 2 f6, f7, plus f7 squared plus 1. Okay. Now, is there any way I could try to say, I want this thing, can you simplify something? Can we use anything we know from before and reduce it down to, if only I had this, then I'd be happy?
the F5, F7, and the F6, F8, even though we don't have that base case.
Interesting. Wait a second. This is pretty neat. I'm just collecting some stuff. Let's not select the one. The one is weird right now. Are you saying that the f6, f8 thing has something to do with an f7 squared?
Uh-huh.
Yes. So now this is actually making us think, maybe we want to prove the whole thing by induction, where we go n to n plus 1. Or like strong induction. Does that make sense? Actually, when in doubt. Oh, sorry? Yeah, let's do it. So actually, by the way, you'll never lose anything by using strong induction. I oftentimes prove things by using strongest induction. Strongest induction means assume every smaller thing is true. Actually, that's the same as strong induction. But I often just go and say, if it's smaller, it's true. All right? That's how induction always works. So neat. You would be able to somehow say, well, I know some of these are already what they should be. Oh, this is really neat. So what do I actually know? So I'm supposed to prove that thing, right? So it's equivalent to this. Let's draw some arrows, because the way I often do things is I try to have the truth go in a certain direction. All right? So I want to get to the green thing. I always draw arrows to say, well, if something else was true, then the next thing is true. Okay? And one way you can do this is you can say, I know how to rewrite F5, F7 by this inductive hypothesis. The inductive hypothesis tells me that F5, F7 is F6 squared plus 1. That was this. Okay? Now I'm going to leave the old F5, F8. I'll leave the plus F6, F7. And now for the other one, I'm going to do plus. I'm actually going to say, I know from my strongest induction that this is F7 squared minus 1. All right? We're doing the pluses and the minuses together. What that actually means is I need to prove it not only for 7, but also for 8. Yeah, and we can also cancel out an F6. Yes, good. F6, F7 will also cancel from both sides. We're going to do a ton of canceling in a second. Now I'm going to write this as F6 squared. I'm leaving the whole right side alone. F6, F7 plus F7 squared plus 1. Okay? Now, the next thing I'm going to do is I'll say, now we can do a lot of canceling. Because, oh yeah, the way that, why this up arrow is true is this is by the strong induction. Strong induction hypothesis. Hypotheses. There's two. We use like two induction hypotheses here. We use like for two different values. So if I'm going up, now I can do a big old cancellation because there's an F6 squared here. Cancels the F6 squared there. And the F7 squared cancels the F7 squared. And then you have this F6, F7, which cancels one of the F6, F7s. And so what I will have is, continuing this flow of logic as I go up. If the next thing was true, then the previous thing is true. Oh, there's all these ones and minus ones. Those cancel. So the plus 1 and minus 1 cancels on the left. And I will have what I want as long as F5, F8 happens to be equal to F6, F7 plus 1. Are people okay with this? It's like, if I had this last line, why is the previous line true? Well, it's because I just like add and subtract the same things from both sides. Yeah? So whenever I do these things, I always keep track of what is the flow of the logic. Even though we're deducing, we're going downward, being like, well, if only this was true, if only this was true. I keep track of the arrow. And it's true that if I have the last thing true, then I can go all the way up. But oh no, this is bad. F5, F8, that's like worse. If you can see, I got myself in a worse space. I'm supposed to prove something about F something and F the something plus 2. And what I need to prove that has a plus 3. That's not fun. Although, by the way, before we go to Zhejia's idea, I want to say, I didn't know that. Is that true? F5, F8 equals F6, F7 plus 1? That sounds cool. Let's double check. I just want to know, all right? I want to know if it's true. I mean, it has to be true, unless we made a mistake. F5, F8 multiplied is supposedly equal to F6, F7, and then plus 1. What's 5 times 21? Let's use different colors. 5 times 21, I know how to do that. That's 105. And 8 times 13, I don't know how to do that. I'll do it in my head for 104. Cool. Okay, it's true. That's not how you do induction, by the way. You cannot do induction by saying we just short circuit over there, we multiply them, it works. But we found another interesting fact about Fibonacci sequences, which is cool. Now, Zhejia, you were going to say something.
What if we split F8 into F7 plus F6?
All right, let's do that. So the way we do this is let's pull it back one more. If only I could get F5 times F6 plus F7 to be equal to F6 times F7 plus 1. Then I'll be happy, right? Because that is what F8 is. Now what? Brayden.
If we expand that out, we have an F5, F7 term, and then we can cite our induction hypothesis again with another
Okay.
plus 1.
So that's the same as. It's actually equivalent. I could go both ways, okay? So, but I'll just write the flow that I care about. This is F5, F6 plus F5, F7 is equal to F6, F7 plus 1, okay? And now let's like cite the induction hypothesis again. We know something about F5, F7, right? F5, F7, that's supposed to be, well, it was F5, F6. I'm writing it faster now. F5, F6 plus, that was supposed to be F6 squared. The odd one is plus 1, okay? Could that possibly be equal to F6, F7 plus 1? The thing that should make you happy, by the way, is that I have less and less terms. And the terms are getting indexes, the numbers at the bottom, getting closer and closer together. This is called the brute force bashing method of proving this particular thing by induction. We should be able to get them equal at some point. How? Can we get it? Actually, I think we can get it. Ling Wei.
I think we can like also split F7 on the right-hand side into like F5 plus F6.
Let's do that at the same time. That'll save us
Get
space.
the same thing.
Yeah. F5 plus F6 plus 1. Oh, and it's equal. It's good. It's good. They're equal. Yes. That's how happy you are when you get to the bottom. Yes, they're equal. We did all this. We got to equal stuff. So now we have proved it for 7. Therefore, it's got to be true for everything. And by the way, this is generally good logic. The way that we know we could do this for everything is you just go and say, what did we actually do here that has anything special to do with 7? The important thing about this analysis is we never divided anything by 2. Like we never took an index and divided it by 2. We never took the square root of an index. In fact, all that ever happened with these like 5, 6, 7, 8s is they only like shifted left and right by about 1 each. So actually, this works. What we've just written here works for all odd values of 7. I mean, if you just made up a new letter of the alphabet called, it looks like a 7, and it just stands for any odd number you have. Yes, Chris, it works for all odd values of 7. That's correct. But I mean, like, this actually, I'm going to say because we ran out of time, this actually works for all of the odd cases. There's a raised hand by Miguel.
Yeah, I'm just wondering, like, the way you did this is, like, kind of unconventional, like, concept, because, like, we're kind of used to having, like, not knowing what the index is, right? We just know, like, it's n and then plus 1. I guess in, like, in the scope of this class, would it be okay to use, like, kind of prove it through this way? That
Yes.
you did, like, through, like, certain indexes?
Yes.
Which is, I know it's a little bit weird to think about it that way, but yeah.
Yes, by the way, this is also how I think of all induction proofs. I find it very confusing to already put an n because you can't tell anything special about the n. It just looks like an n. But if you write a number, the only thing I want to make sure is that I never did anything weird like take the square root of the number or divide the number by 2 in a way that might not generalize. What I'm trying to say is you write this out first, okay? And since this is not a concepts class, I'm okay if this ends up being like, yes, you proved it for 7. And the idea of did you cheat when proving it for 7 is going back and looking at specific numbers, that's cheating. Cheating is called, how could you generalize that? Do you know what I mean? It's like, I can't generalize that for 770. Actually, that's not an odd value, 771. But if I looked at this and I had, instead of 7, I had 771, is it obvious what you would change everywhere? Do you know what I mean? Like, what is obvious here is if I want to change these to different numbers, I simply take all of those indexes and I just shift them all by the same thing. But the important thing, yeah, go on.
Oh, no, I was just agreeing with you.
Yep. And actually the way I'm okay with a proof is if you say, this is it for 7. Notice I said one important thing. It did use the oddness of 7. The way we use the oddness of 7 is that occasionally we wrote like a +1 instead of like a -1. This +1 is only legitimate because 7 is odd. If 7 was even, it would be a -1. Does that make sense? So I have 2 cases, 7 and 8. And I have to do these 2 cases, and I have to see that in each of these cases, if I wanted any other arbitrary number, I either choose the odd thing or the even thing. And I shift all the indices, like just like shoving it like a car in one direction. And saying like it generalizes, and it's obvious that it generalizes is good enough. Okay, so that finishes this part. I will say I actually had a completely different proof in mind, and we'll do that next time. And you'll see that there's like other ways to try to solve these problems. There's a way that doesn't involve any induction at all, and we'll do that next time. So, thanks everyone. Yeah.
Thank you.
Thank you.